Hello, my name is Robert Pittman. I'm an electrical engineer from Sacramento. I'm founder and managing partner of a 20-year-old consulting firm, and I'm developer and publisher of PV Rocket, solar engineering software to create your construction documents faster and more accurately. I'm going to create a series of videos that breaks down the calculations that PV Rocket performs and shows you where they come from in the code, the National Electric Code, and why they're required. Before I do that, I want to start with the basics, not make any assumptions. I'm not going to go over what alternating current is versus direct current, calculations like wattage to amperage, depending on what voltage you're at. There's plenty of YouTube videos out there for that, but at the same time, I'm not going to make any assumptions about solar, and just start from the basics, and there we go. So let's start. What we're talking about is PV modules, the black modules that you see up on people's roofs, and they have a certain characteristic associated with them: voltage and current. I'm going to create just a couple of assumptions here. Every module is different, and they're measured at what's called the standard test conditions that we'll talk about in just a second. And they produce direct current, DC, 45 volts, 6.7 amps at the standard test conditions. So to get them useful, get that power useful out of our outlets, your outlet is 120 volt and so forth. We need to convert it, and we use an inverter that takes DC in and creates AC out. And this is the most basic system, and it's called a microinverter. Microinverters are small. Think of the size of a book mounted to the back of the module. And usually they're 1-for-1. So if you have a module, you have a microinverter. Some microinverters will accept 2 inputs from 2 modules. Some microinverters will accept 4 inputs from 4 different modules. But the concept remains the same. Just modules in, AC power out. It could be 120 volt out, could be 208 volt out, and so forth. And the way that it works is you put them together, several microinverters, and you come out with a circuit that you can take into a panel at your house or so forth. I believe I have 13 modules on my roof, and I use microinverters at my house. I didn't design it, so I'm sure they're microinverters, but I'm not sure what, well, they're in phase. So it's probably 1-for-1. And I believe that microinverters are typically about 2 amps output. I might be making an assumption there, but if I have 13, that means there's 2 circuits that tie into the panel. They could also be produced at 240 volt, and might be 1 circuit then at that point. The equations that dictate all of this is Ohm's law, V equals IR, and then you've got watts equals voltamps times a power factor, where the power factor is less than or equal to 1. And then you've got watts divided by voltage equals the amperage. Typical values for the volts are 120, 208, 277, 480. These are all single phase values. And then you've got 360, 831, and then the less common is 240 and 415. Like I said, I'm not going to go into that. Another way of doing The next style of system is called a string inverter. And what we do there is we take the same modules and we put them together in a DC circuit referred to as a string. If each module has the same characteristics as I mentioned before, 45 volts and 6.7 amps, then the output of this will be the combination of 45 plus 45 plus 45 plus 45, which is 180 volts, and the current remains fixed at 6.7 amps. And this goes into a string inverter. AC out. And the string inverter can receive multiple inputs from multiple strings and could be as high as 60 kW is a popular one, and now they're starting to produce ones as large as 100 kW. So let's talk about safety on the DC side. There are 4 ways that we can guarantee the safetiness of this. So what size conductor do you put on something like this? It's 6.7 amps. There's a few safety factors that come in. A lot of strings could be sized at number 12, but typically our customers require number 10 on their DC conductors. So how can we guarantee that those are the right wire sizes? Somebody might ask you, well, what is the system producing? And your answer would be, I don't know. We have to. It depends on how much light is incident on the system, the temperature outside, all these different factors. So we size things for worst case scenario, and the first safety factor is the standard test conditions. So if I switch over to the internet here and pull up a cut sheet, I have a Trina Solar cut sheet that has 5 different modules on the same cut sheet. So if we look at the 350 watt nominal power one, and well, all of these actually, if you look down here at the STC, it says the irradiance, which is the amount of light coming onto the module, is 1,000 watts per square meter, and the temperature is 25 degrees Celsius, and then it gives an air mass. Those are the standard test conditions. And why is that a safety factor? Because it started off just being able to compare one module to the other. So to get apples to apples comparison of what the modules are able to produce, they had to be able to standardize the test conditions, and that's what they did. The reason it's a safety factor, though, is that 1,000 watts per square meter is a really, really bright day, and a cell temperature of 25 degrees Celsius is a relatively cool day. And those two things usually don't go together. If it's bright, it's summertime, and it's hot. And the temperature, the operating temperature, affects the output. In fact, I can scroll down here, and there's another set of charts based on the NOCT, which is normal operating cell temperature. And you can see that the standard test condition of this module is 350 watt. The normal operating cell temperature is almost 100 watts less, and the irradiance that they use is 800 watts per square meter, which is not as bright, and they actually bring it down to 20 degrees Celsius. So they must be taking an average there between summer and winter and figuring out what's realistic on an average. Yeah, they also show a wind speed here of 1 meter per second, because the wind speed can cool the modules also. So back to the discussion about safety. Standard test conditions is a level of safety. Another level of safety is short circuit and open circuit. So when I say there's 45 volts and 6.7 is the standard test conditions output, the 45 volts is an open circuit voltage, which is the worst case voltage that you'll ever read. It's not connected to anything. It's not influenced by the load. It's open, just two wires out. What is the potential difference between them? That's 45 volts. That's the worst case. The 6.7 amps is the opposite of that. It's a short circuit current is what we're required to use in the calculations. 6.7 amps at short circuit, that's no load, no nothing, just put the wires together, 6.7 amps. So that's the opposite of open circuit. So by running our calculations at short circuit and open circuit simultaneously is a level of safety factor on our DC wire sizes. Another safety factor is a coefficient. So the manufacturer will give a coefficient for every module and say if you live in an area of the world that is very cool, you have to increase that voltage to compensate for it. And by the way, I haven't mentioned string length yet. We'll get back to that in just a second, but I'm going to write it down. String length. So how many of these modules can we put together? I showed 4. That's ridiculous. Normally there's 16, 18, 20, some can be as long as 21, 22 modules long. What is the limiting factor on string length? And we'll get to that in just a second. So there's a coefficient that you add to the calculations to make sure that you've compensated for your area. So standard test conditions, short circuit, open circuit values are all fixed for in a lab. The coefficient compensates for where you are on the planet. The fourth one is 25% safety factor that you have to add to everything because it's a continuous load. It runs for 3 hours or longer, and the National Electric Code requires a 25%. Okay, great, but there's another 25% safety factor that after you've measured the standard test conditions, the short circuit, open circuit values, multiplied in the coefficient, just to make extra sure, they throw on another 25%, which the two 25% together equals 156, 1.56, or 156%. So let's go back to string length then. What is the limiting factor on how many modules you can put together on a DC circuit or a string? The limiting factor is this total voltage value. There's a limit for residential. It's typically 600 volts, and this is not in the code, I don't believe. This is dictated by fire marshals, like the California State Fire Marshal or your fire marshal in your area. For commercial and industrial, the limit is 1,000 volts. And for utility scale, the limit is constantly being pushed. 1,500 is common. I believe they're headed to 2,000 volts and so forth. And we'll talk about why. Cost effective and efficiency. We'll talk about that in just a second. Longer string lengths lend themselves to reduced cost of installation. So these are string inverters. The third common style is a central inverter. And central inverters are, we used to call them megawatt in a box. You can get them any size, megawatt, 2 megawatts, 3 megawatts, and so forth. So they are central, and you can have your strings out here. I'm only going to draw 2. And through a fuse or something, you bring them into a DC combiner panel. This is often the way it's done. And you can do as many of these as you need to get up to the wattage of the inverter or the system. And then you bring these into the central inverter. Notice that in our case we did 4, and we said that they were 180 volts in. But we said that the 6.7 amps was fixed. Well, when you combine them up in parallel like this, the 6.7 is added by the number of strings that you put together. So in this case we have 3, so we have 20.1 amps that would be going into there. And on the top one we had 4, so we would have 26.8 amps going into that one. So wattage equals volt amps, like I said at the start, volts times amps. So each small module produces a certain amount given on the cut sheet. I said hypothetically 45 volts or 6.7 amps. And the way to do it cost effectively, efficiently, is to combine them into strings and get them into the inverter one way or another, directly like I did on the string inverter, or by combining them up into DC combiners like I showed here on the central inverter.